Yeah.
Maybe I could. I mean, maybe if I just say, David Gross, who runs the Kavli Institute of Theoretical Physics in Santa Barbara, was our Rothschild visiting professor in one of the programs about 6 months ago, and he came here obviously with. Is this being recorded? Yes, I guess it is. So David came here very interested in the processes that run at the institute and how we work things. And he brought a great idea of actually, which he has initiated at Santa Barbara, of bringing the programs that are running at his institute together, talks which are meant to be sufficiently general that the other program can become engaged. And he said, you really ought to try it here. We did, it was a great success, and I'm looking forward to another one this afternoon. Over to you, Dave.
Okay, thank you. Right, so that's what I'm going to try to do in this 45 minutes, is just give you kind of a coffee table picture book kind of look at some of the ideas that we're thinking about in the Combinatorics and Statistical Mechanics program. And I'm certainly not going to do anything in great detail. It's going to be kind of impressionistic, broad brush, conceptual, I hope. And at the very least, I should expose you to some of the language if you come across it in your broader mathematical reading or something. You'll maybe hang an idea on the words, and as a result. But I have to start with something reasonably concrete so that you have something to think about as we go through the kind of the ideas. So I'm going to start off with the Ising model, or Ising model, which is kind of a good starting point for the kinds of things we think about. So this is originally a very simplified model of a ferromagnet. So it's meant to describe at a microscopic level what's happening inside a magnet. But it's very abstracted. So you can define it on any graph. And often the graph is taken to be some large square grid. You think of this as representing a crystal lattice or something. You've got an atom at every corner of this grid. And the atom can be in one of two states. It's got a little magnetic dipole, a little magnet that can have its north end pointing up or pointing down. So just designate those as a plus spin and a minus spin. So a spin configuration is just a function from the vertices of this graph to +1 and -1. And you've got a plus here, minus here, plus, minus, plus, minus. Something like this. Every vertex gets a little plus or minus describing whether the atom is spin up or spin down. And there's an energy associated with every configuration that depends on a couple of parameters. H of sigma is, there's minus signs in here for some reason. Okay, so what all this means is this kind of thing is called a Hamiltonian. And that word used to scare me until I realized it's just an energy that's associated to the spin configuration. So what this term is doing is it's an interaction between vertices v and w that are adjacent. That's what I mean by this notation in the graph. So here's a vertex v and an adjacent vertex w. And whenever they're adjacent, you compare the two spins on these two sites, and you get either a plus j or a minus j, depending on whether the spins are opposite or the same. Because this product will be either plus or minus 1. And this parameter j here is a material constant that is describing something about the material in question. It's just the interaction potential on a single edge. This term here doesn't involve any interaction between vertices. It just looks at every vertex in turn, and it counts up the total number of plus spins minus the total number of negative spins. So it's just counting the bias between how many spins are in the plus direction and how many spins are in the minus direction. And this parameter here is kind of a measure of the strength of an external magnetic field. So this J is an interaction potential, and H is an external field. So there's one more physically relevant variable, and that's the temperature at which this thing is sitting. So T is going to be the temperature in absolute degrees Kelvin, absolute temperature. And beta is 1 over Boltzmann constant times T. Now the reason for this, if you want to explain the reason why this model is physically sensible, I mean, it's the kind of thing that takes chapters. But we can just sort of use it as a definition of a model. It's the Boltzmann-Gibbs or ergodic hypothesis, I guess, that over a sufficiently long time, the system is in state sigma for a time proportional to e to the minus beta this energy. So this we can just take as an axiom of the system, but the physical justification for it is rather detailed. And so the idea is that these spins on the atoms in this graph are flipping back and forth rather rapidly compared to the time span on which we observe it, and we just sort of look at the time average over a sufficiently long time, then on average, the system will be in a particular state sigma for a time proportional to this number called the Boltzmann weight. So in order to define a probability distribution, we have to normalize things so the sum of the probabilities is 1. So we just sum these things over all possible states. And that gives the partition function. I'll call it Z of G. It's the sum over all spin configurations of the Boltzmann weight of that configuration. So that's kind of a very quick description of the Ising model. And this idea of a partition function is much more general than the Ising model itself. Basically, it's just a recipe for defining a family of probability measures on the set of all configurations. So you can take it, and this is kind of a recent trend in combinatorics, is to lift this template away from any physical interpretation and say, I have some set of configurations of combinatorial interest. define some natural energy function on that set of configurations and plug that into this Boltzmann-Gibbs formalism. Then you get a collection of probability measures on your set of combinatorial configurations. And you can kind of take the philosophy of statistical mechanics and transport it into other situations.
A quick question. Did you assert that the partition function is a distribution, and is that obvious?
Then you define the probability, I guess, just by normalizing.
Normalizing constant? Okay, never mind, that's fine.
Okay, so it's proportional to this, and the normalizing constant is this in the denominator.
Right, I understand.
And everything's finite at the moment, so it's really well defined. Okay. Maybe one thing to notice about this is that it favors configurations of low energy. The smaller h is, the bigger this is. So configurations at low energy will be favored. And the interaction potential can have either sign. If the interaction potential is positive, then this term will be smaller when the spins are the same, when interacting spins are the same. That's the ferromagnetic situation. Ferromagnetic. In case this interaction potential is positive, adjacent spins like to be in the same direction. And in the other case, they like to be in opposite directions. It's called antiferromagnetic. So I'm going to be talking about the ferromagnetic case today. Okay. So what does one want to do with this kind of setup? Well, it was originally devised in the 19th century to explain thermodynamic quantities. You can calculate things of thermodynamic interest from the partition function. For example, the spontaneous magnetization. It's called m naught. It's the expected value of a spin. And if you work out this, you'll see it's minus 1 over beta, 1 over n if there are n vertices, the derivative with respect to the magnetic field of the logarithm of z. So this is about as complicated an expression as I'm going to write today. So n is equal to the number of vertices. If you do this logarithmic derivative, you'll discover that taking the derivative of this with respect to the small h, you get exactly the average value of any particular spin averaged over all configurations. This is the average spin at any one site. So it's going to take a value between -1 and +1. And macroscopically, you can think of it as the fraction of spins that are in the plus state minus the fraction of spins that are in the negative state. So this is a macroscopic observable quantity that is calculated from this microscopic information, the partition function. And we like to say what it looks like. And so it's a function of the temperature, or this inverse temperature beta, and it's also a function of the external magnetic field. And I guess it's also a function of the interaction potential J, but you can say normalize things to set J equals 1. So qualitatively, here's what happens. Draw a graph of magnetization versus the applied field. There's a range of qualitative behaviors. Different things happen at different temperatures. So really, you should try to imagine a three-dimensional graph, which I didn't want to try drawing a surface in 3 space. So I'll give you a slice here when the temperature T is very high, and another slice here when the temperature T is very low. At a very, very high temperature T, well, the magnetization is always between 1 and -1. It's just going to vary smoothly. If the applied magnetic field is very high, then most of the spins will end up at +1. If the applied magnetic field is very strongly negative, most of the little spins on the atoms will be -1. And you get this smooth curve in between because the temperature is high. If the temperature is low, something qualitatively different happens. Again, if the applied field is very strong, most of the spins will be +1s. But as the field is lowered to 0 field, you still have, well, you have an intercept at a positive residual magnetization. And the graph is symmetrical because the positive and negative field symmetry. So this kind of discontinuity here, well, it can't really happen for a finite system. So, because this is an analytic function of everything. So this kind of discontinuity happens only in the thermodynamic limit, it's called. And that's the limit of an infinite system, of a sequence of bigger and bigger systems like this. So. Now, what about an intermediate temperature? I mean, as you decrease the temperature, and you look at this graph, this gap decreases until you get to one particular temperature in the middle, at which the graph becomes continuous, but the derivative at the origin diverges. So this is at T equals Tc, critical temperature. So at the critical temperature, it's a continuous curve, but the derivative is infinite at the origin. That happens at precisely one value of the temperature. And this is the kind of qualitative behavior of what the spontaneous magnetization is doing. But we'd like quantitative versions of that. And so we'd like to be able to compute what the critical temperature is, for instance, and a lot more detailed structure about what happens there, and things like that. So the issue becomes how to compute this partition function and how to take the thermodynamic limit. I should say something about the thermodynamic limit. You take a sequence of graphs, each one contained in the next, and all contained in gamma, which is the union of them all. So you can say everything of a thermodynamic nature can be computed from the following. So if you look at the definition of the spontaneous magnetization I gave there, you see that 1 over n log z of g, which is what I've got here for one particular graph. Now, as the sequence of graphs becomes larger and larger, for instance, I get the entire infinite square grid in the limit. And this is no longer, this is no longer analytic everywhere. It can have singularities at various points for various beta and h. And those will be singularities at points where this partition function is 0. Yes?
Is there a derivative missing?
No, there's no derivative missing. In general, say in the thermodynamic limit, you would define the spontaneous magnetization to be the partial by h of the free energy. So this free energy is the key to all the thermodynamic quantities that you want to compute. You basically get all of the observable quantities as partial derivatives of the free energy with respect to certain of the control parameters. So it's a remarkably subtle question as to when this free energy limit exists. And it's quite intricate. It involves some quite fancy enumerative combinatorics, and also some structural properties of the graph that you get in the limit. So there's a nice interplay of quantitative graph theory that goes into finding a good radius of convergence, for example, for the free energy. Okay, so this kind of phase transition happens in this model at low temperature. This doesn't count as a phase transition because the spontaneous magnetization is an analytic function everywhere. So the phase transition comes about at points where the free energy fails to be analytic. And if you look at the way it's defined, this can fail to be analytic only at an accumulation point of the set of singularities of this logarithm. And so this logarithm is singular exactly where the partition function is 0. So to locate phase transitions in statistical mechanics models, you look at a sequence of graphs tending up to the limit graph, and you look at the partition functions of each of those finite pieces, and you look at the zeros of all of those partition functions, and you look at the accumulation points of that set of zeros. Those accumulation points tell you where the phase transitions occur. And of course, doing all of that quantitatively takes a good deal of work. So accumulation points of set of zeros of all ZGK, points of phase transition. So this is the Li-Yang picture of phase transitions from the 1950s. Well, if this is the kind of information we want, it becomes important to get a handle on what this partition function is, really. And that requires, well, you see in this Ising model, it's defined as a sum over 2 to the n states where n is the number of vertices in the graph. So this is a huge unmanageable sum of things. And it's only possible to compute these partition functions in some special cases. Other approaches to exact computation are to do Monte Carlo simulations. If one can sample from this Boltzmann-Gibbs distribution effectively, then you can simulate this kind of dynamics and get accurate approximations. But if you want to compute the partition function exactly, there's a very clever method that goes back to Onziger in the 1940s. I think he was the first one to use it. So this is the transfer matrix method. This is a very nice idea. Take a big patch of the square grid. And cut out a little piece of it, like this. Let's see. Oh, I've gone too far. And I'm going to let this rectangle bound the finite piece that I'm going to calculate the partition function of. And then I'll let the rectangle get bigger and bigger. Eventually I'll get the entire square grid in the limit. So let's say there are n sites along here, and I guess I should have gone to here. L sites along here. And I'm going to impose what's called toroidal boundary conditions by identifying this side of the rectangle with this side. So every vertex here will be identified with the corresponding vertex. I've done something funny again. Well, we'll be identified with the corresponding vertex here, so I guess I'm not wrapping it around properly. Oh, but I need these as well. So my picture is a bit off. I'll just look at two levels in the middle here. So you have this level 3 and this level here. So I do need that. Now the idea is that in order to understand how everything is working in this region, I only really need to understand what's happening between these two levels here. And then I can repeat that argument between these two levels here. And then I can repeat the argument again between these two levels here, because of symmetries of this torus as you move along here. So what you do is you encode these possible spins here, plus, minus, minus, say. There are 2 to the n possible n tuples of spins here, where the width of this torus is n. And there are 2 to the n possible n tuples of spins here, minus, plus, minus, for instance. So you encode all of those possibilities in a 2 to the n by 2 to the n matrix. So the entries of this matrix are, you look at the row index, that's some n tuple of spins here. You look at the column index, that's some n tuple of spins here. And the entry of the matrix is the contribution to the energy of this part of the graph only. Now, if you can compute this matrix, then you can compute the partition function. What you do is you look at whatever the spins are on this end of the torus, then you look at, you think of that as a particular vector, a column vector of spins. Or if you apply the matrix A, then it will give you the contribution of these edges to the energy. If you apply the matrix A again, it'll give you the contribution of these edges. So for instance, if I know the spins here and I know the spins here, if I sum over all the spins here, that'll give me this much of the partition function. So if I start here and I apply the matrix L times, it will get me from this end all the way up to this end. That's why it's called the transfer matrix, I guess. But if we're assuming that I've identified this end with this end, then the spins here have to be the same as the spins here. And you can guarantee that algebraically by taking the trace of this. And this, if you work out the linear algebra, is exactly the partition function here. So this changes the game now a little bit. Instead of having a sum over a huge number of spins, I have to compute a single matrix and then find the trace of powers of that matrix. And that can be done if you know, say, the eigenvalues and eigenvectors of the matrix A. So it looks like that might be replacing one hard problem by an even harder problem, but it's an amazing fact that, well, I don't know how Onziger actually did it, but he just wrote down a complete set of eigenvectors for A and the associated eigenvalues. And so you get a formula for these partition functions like that. That gives you a handle on these partition functions from which you can calculate all the rest of these things. I should say that there's an essential ingredient in being able to do that, which is called the Yang-Baxter equation, about which I will say nothing more. So I just wanted to, yeah.
If you lose the grid, how bad does it get?
Well, you could do a similar kind of thing on a triangular grid, for instance.
I see.
And actually, people have adopted this idea in graph theory, computing chromatic polynomials, which is a partition function for a different model. And the essential thing is just that you need something like this that you can repeat over and over again. So you just need some local piece, B, and another copy of it, B prime, and some predictable interaction between them. So this level would be B, this level would be B prime, and it's the same interaction between these two levels as between these two levels. And as long as you have that repetition and these two ends are identified, this formula will hold.
It seems like a very restrictive requirement.
Well, combinatorially it is, and physically it's not, because our interests are complementary in this issue. A graph theorist looks at a problem like this and thinks, these partition functions can tell me something about the graph. And a physicist looks at problems like this and says, I can use any graph I want because in the limit, at criticality, it doesn't matter what graph I use, which is kind of surprising. That's called the universality, and it's a hypothesis that's been well tested but not proved. So if you have a two-dimensional grid, it doesn't matter if it's a square grid or a triangular grid. For some questions, you'll get the same results. For other questions, there are there are specific differences.
Yes,
But
I
this,
mean, the restriction, is it not true from the physical point of view, is that when you have this regular lattice, and the fact that B and B primed are the same is just equivalent to saying the system is translation invariant. So you're using the translation invariance of the lattice as a kind of natural thing in the physics. That's the sort of physical motivation anyway.
yes, yes. And so physically you expect it to only depend on the symmetry of the lattice and the dimensionality of the lattice. And other microscopic details are unimportant. Okay, so to wrap up, well, I'll just maybe say go one level beyond this spontaneous magnetization and talk about correlations. So this would be the probability of finding two spins in the same state minus the probability that they're in opposite states for a given pair of vertices V and W, or V and W are fixed and say separated by distance r. So this is the correlation between spins V and W. And you expect at high temperature this should go roughly like e to the minus r over c at high temperature. Now, what this means is that at high temperature, the spins are jumping back and forth very quickly, and the influence of one spin being in a plus state can't affect things very far away. So there's an exponential decay to the correlation between two spins. This c is called the correlation length. An interesting thing happens at high temperature. You've got a finite correlation length. As you reduce the temperature to the critical temperature, the correlation length becomes longer and longer, and at the critical temperature, it actually diverges to infinity. So the critical temperature, at the critical temperature, the correlation length is infinite, and every spin has a measurable effect on every other spin, which is kind of counterintuitive. And so you get a different decay rate. You get r to the minus eta at criticality. So figuring out what these correlation lengths are and what these critical exponents are is an important part of the game for physics. And it's something that I think people haven't even begun to think about in combinatorics, but is bound to be of interest in more generality. So the qualitative behavior of the Ising model at exactly the critical temperature is extremely interesting. Not only do you have the translation invariance and rotation invariance, but because of this infinite correlation length, you've also got a dilation invariance. It doesn't matter at which scale you look, you can renormalize the parameters to get exactly the same functional form. And you can do that locally, so it's not just scale invariant globally, but locally. And so the combination of those symmetries is what's called conformal invariance. And conformally invariant theories allow you to predict a lot of structure about what these critical exponents look like and how they're related to one another. And that is getting pretty close to the edge of technology at the moment. So I think it's a good place to stop.
Just to check, where are you going to have, where is the next talk scheduled to begin?
15 minutes from now.
Going to have a break for tea or just questions? How are you planning it?
We can have questions and then we can just have a short breather.
Okay, great. I have a question. I mean, this used to be my meat and drink.
Yes.
I made a living on this kind of thing, and it's great. So can you or anyone explain to me what's in it for the combinatorialists? I mean, they get a great set of problems, right? Only some of which have actually been cracked, and they're still, through this conformal event, etc. It's been huge progress. But what's in it for the combinatorialists, and are there any applications of this kind of thing which outside of physics, which the combinatorialists are interested in?
Well, I think what's in it mostly is a way of looking at things. It's the idea of looking at this partition function and this Boltzmann-Gibbs distribution, not attached to any particular physical model, but to use it as a tool to analyze purely combinatorial models. So for instance, if the configuration space is the set of all subgraphs of a given graph, and the energy or the Hamiltonian is cooked up to correspond to certain natural pieces of information that one would like to know about the subgraph, like the degrees of the vertices and the number of connected components and so forth, then you can take that information, the configuration space and the Hamiltonian, and plug it into this formalism, and you get a probability space for this set of combinatorial objects, not just the set itself. So it's extra structure in which we can look at a set of combinatorial objects and ask analogous questions. Then you get a kind of a quasi-physical combinatorics. And I think that's what's in it for us. It's a whole new world, really. It's a new way of looking at things.
There are three very natural connections with statistical thinking. One, of course, is that this Ising model and non-lattice representations of it are exactly what drives all the conditional autoregressive spatial models. And those are very
what?
cool.
Sorry, David?
CAR models, conditional autoregressive models.
Right.
And those are used for describing how insects might spread through a cornfield or something like that. And there it's sort of square because the corn is planted regularly, but you could imagine disease in a suburb where it's much less lattice-like.
Yes, these kinds of models have been analyzed in statistical mechanics too. In fact, traffic is another application. So all of these kinds of things where you have a large number of agents kind of maneuvering around a local environment, interacting with one another, they all fall into this pattern.
That actually brings me to my third. There's distributions on combinatorial objects. And there you want to move away, I think, or at least statisticians want to move away from unimodal distributions and get a richer family with so forth. But this is a type of tool that would be used as a building block. But the one that we don't have an answer for, but which I think is implicit in what you're saying, are agent-based models. Agent-based models are very, very cool in many parts of the communities we talk to. And there's virtually no statistical understanding of the uncertainty associated with these models. Mm-hmm. But if you think about the agents as being lattice points and the rules for their interaction being like an easy model, then it seems to me that there's some hope for describing distributional properties of agent-based models.
I think that's probably true because if you don't like the lattice, what you can do is say the length of this edge is A, and then let A tend to 0. And then you get a continuum limit.
I was actually thinking the agent-based models could work very nicely on something lattice-like.
Yes, well, that's right.
You can think of each of those little.
Then you get a very nice Hilbert space of states on a lattice model, because you've only got you've got a countable number of places where things can be, and so it's easy to describe that way. And if you let the lattice spacing tend to 0, this goes by the name of renormalization group techniques. You can let the parameters in the model be a function of A if they're done in precisely the right way, you get a continuum limit model, and things would work out very well.
Okay.
One place where, I mean, the Ising model was
Over your head, David.
adopted as the model for pixelated binary images in statistical image analysis by Stuart and Don Geeman in particular.
Mm-hmm.
So you have the idea of a black and white image is likely to show local spatial correlation.
Yes, yes.
So the Ising model is the key, is the elementary one for binary images, black and white images, and the Potts model for multicolored images.
Uh-huh.
So then it's assumed that what you actually see is a noisy version of that. So you get noise added onto a realization from the Ising model as a possible model for image analysis.
I see. Yes. Interesting application. Yeah.
To deal with that, they kind of developed what they called Gibbs sampling in Monte Carlo, which I think is otherwise known as a heat bath.
Yes, and we're going to have a workshop on that the last week of this month. That's exactly what it'll be about.
Is there, could I ask, I mean, in the, where this impinges on the games that you guys play, is there a special role for these, the special situations where the parameters are such that you don't have exponential decay, or before the exponential decay sets in, there are large length scales of highly correlated regions, with a lot of degrees of freedom interacting together? That's the, that's the really hard bit for a physicist to handle, actually, and that's where a lot of the interesting physics comes in. So do you get limits like that, special cases? Does that make any sense?
Well, I suppose you might, with certain, if the statistician would say, here's a real picture. Let's try and fit an appropriate model, which would involve estimating the temperature parameter, for instance. Obviously, it's not a trivial task to do that, but I suppose you might get into difficulties if your estimate of the temperature parameter looks like it might be at or beyond the critical point.
Mm-hmm. Yeah, that brings up an issue that I didn't have any time to talk about, which was if you look at these regions of positive spin or negative spin, what do they look like? What's the shape of the boundary between them? It turns out to be a fractal whose fractal dimension can be related to the applied fields and temperatures. So if one is able to measure approximately measure the fractal dimension of the boundaries, then you could estimate the temperature of the system. Yeah.
We have a short break and restart
Yes.
at 4:15?
Yes.
Who's going to do the 4:15 one, is that? Mike?
Don't hurry back.
Great, thanks very much.
Thank you.